Hello there, I think it's time to begin. So I'm just going to set myself up and then we'll be ready to go. Thank you, Harry, for asking. Rags is fine. I think there's every chance at some point during this hour that she'll interrupt us. It seems to be her speciality. It's very nice to see you all again. I think we've got 13, maybe 14 in the room. Really admire your loyalty, even after what feels like an age since you're actually at school. I'm still glad you want to finish this course and learn some more physics. So what we're doing today is really the second half of a lesson. So I'm not going to put up a new title. You can just carry on from where you were in your books. And we're going to do about 3 things. We're going to do one of my 10-mark quizzes to start. I mentioned that in the comments just before. We'll then go through the answers to that, and you can see what you got out of 10. I'll then do some practice of Fleming's left-hand rule, because I really do think it requires practice on more than one occasion for us to approach something like mastery. And then we're going to come back to the questions I set you last time. The last of which is a superb physics question, but a difficult one. And so it's a really useful one for me to give you some proper time to do it, and then for us to go through it. And that's how we'll end the lesson. I also think, just to wrap up this kind of intro, that we should be comfortably within the hour today. That I'm not expecting this to overrun, which is good. And bang on cue, Rags is interrupting me. Are you coming in on that, Rags? Here you are. We'll just say hello and then I'll put it down. Rags, do you have anything to say to the class? No? No, she just wanted to say hello, it would seem. So I'm going to put her down. She'll continue to get in my way, no doubt. She looks huge on this screen. She's not that big. But I'll put her down and she can pop in if she wants to say anything later. There we go. So we'll start with a quiz. And as I said in the comments, you can either do this quiz on a spare piece of paper. We tended to do that in class. Or, of course, you can just do it in your book. It doesn't particularly matter now if you've got plenty of space in your book. It's just some people like to keep their books for sort of the actual work rather than this recap work. Write the length of time. Please don't respond in the comments, just respond on paper. We'll go through all the questions at the end of these 10 questions. The first few are from anywhere within the physics topic. The last few are from the most recent work, so it will be a good recap as well. First question is this. What are the units of a moment of a force? So we talk about moments of a force, the turning effect of a force. What is the unit we measure moments in? Please write down your answer to question 1. Rags would be a lad, Harry, but she's a girl. I don't know if girls can still be lads, but that's a whole other feminist argument for another lesson, I think. Question 2, what are the units of volume? So question 1 was what are the units of a moment? Question 2, what are the units of volume? These questions have just been pulled off randomly from the set of questions that I have. What is the name for a method of reducing energy transfers by the use of non-conductive materials? I'm going to say that again, and it's a question that sounds a lot more complex than I think the answer actually is, but I'll leave it to you to decode what the question is asking. So one-word answer, I will say that. What is the name for a method of reducing energy transfers by the use of non-conductive materials? What is the name for a method of reducing energy transfers by the use of non-conductive materials? I suspect you'll either know that or not now, so I'm going to move on to question 3. Again, I'm looking for a one-word answer. What is the name of a scalar quantity that measures how far an object moves? So the answer I'm looking for here is a scalar that describes how far an object moves or how far it is away from another thing. How far an object travels even. But what is the name for that particular scalar quantity? And question 5, I need to know what a phrase means. Latent heat of vaporization. What is that for changing? So when you apply the latent heat of vaporization to something, what effect does that have? When you apply the latent heat of vaporization, what is that changing? I think in those first 5 questions, the wording is likely to be what throws you off, but do your best and we'll go through them very shortly. What is an electromagnet? Conceivably, there's lots of ways to answer that question, so maybe I'll make it a bit more specific. Tell me what an electromagnet is made from. How do you make an electromagnet? Next question, this is question 7. Though I'll pause a minute, I'm not sure I gave you enough time to write. It's very hard for me to judge that when I've not got a class in front of me. But question 6 was Fleming's left-hand rule. Fleming's left-hand rule shows the relative directions of which 3 things. In other words, what do the 3 fingers, or the thumb and the 2 fingers, what do they represent in Fleming's left-hand rule? What is represented by these 3 digits in Fleming's left-hand rule? Question 7. Question 8. Just considering whether to reword it. No, I'll keep it as it is. Question 8 is this. The strength of magnetic field surrounding a conducting wire depends on. So if you have a straight piece of wire, what affects the strength of the magnetic field around it? I hope that's clear. It's when I read back, I thought that wasn't as clear a question as it might seem, but I hope it's clear. That was question 8. Question 9, hopefully a more straightforward one. But what is the name for the 2 places on a magnet where the magnetic forces are strongest? What's the name for the 2 places on a magnet where the magnetic field is at its strongest? And then finally, I'd like you to draw the magnetic field, question 10, around a bar magnet. So I'd like you to draw the magnetic field around a bar magnet. I'll show you on screen by doing a drawing of my own, whether you've got it right or not. But just on your piece of paper, draw the magnetic field around a bar magnet, please. Right, we'll go through those. You're just keeping this score for yourself. I may ask at the end if you want to send me your score in. I'd be intrigued to know how well you have retained this knowledge. But for now, we'll just keep it and mark it for ourselves. Obviously, we can't swap them between us. Some of them, I'll use my little board to illustrate the answer more clearly. But most of them, I can just go through the answer as they are. So the first one was, what are the units of moments of a force? And the answer I hope you got was Newton meters. Of course, you can write the abbreviation NM, capital N, lowercase n. But Newton meters are the units in which we measure moments. Question 2, the units of volume. Volume is measured in meters cubed. Meters cubed, again, you can write it in its shortened form. Question 3, the wording, much more complex, I think, than the answer. The question was, what is the name of a method of reducing energy transfers by the use of a non-conductive material? And I was looking for the answer, insulation. Insulation, that is a non-conductive material, and it reduces the transfer of heat from one place to another. Insulation was the answer there. Next, a very specific answer. What was the name of the scalar quantity that describes how far an object moves, or how far away one object is from another? The word is distance. Again, the answer more simple than the question sounds. Distance is a scalar, and we came across something called displacement, which is its vector version. But distance was the answer there. Question 5, latent heat of vaporization is for changing. Anything that means, and you can word this in different ways, but anything that means going from a liquid to a gas, or the transition between liquid and gas. When you supply latent heat of vaporization to something, it will go from being in a liquid state to a gas state. Anything that means that gives you your answer. Question 6 was, how do you make an electromagnet? Well, as long as your answer described that you need a solenoid, if you didn't use that in words, that's fine. If you mentioned a coil of wire, fine as well. But a solenoid, an iron core, and I would say the best answers would also include a current flowing through the solenoid or through the wire. If you left that off, that's fine, as long as you had solenoid, iron core, but ideally solenoid, iron core, and a flow of current through that wire, through that solenoid. Fleming's left-hand rule shows the relative directions of what things? Well, going from thumb through the fingers, thumb represents the motion, or the force, either word fine, force or motion. First finger represents the magnetic field, and the second finger represents the current or the electric current. So motion or force, magnetic field, electric current. And I hope that was clear. The strength of magnetic field surrounding a conducting wire depends on, well, I think the best answer to that, so I described how we'd have this straight piece of wire, it would have a field around it, a circular field. The strength of that field depends on the size of the current passing down that wire, I think is the best answer. The size of the electric current. Two more. The two places on a magnet where the magnetic forces are strongest, we're talking about the magnetic poles there, the North Pole and the South Pole, but magnetic poles or just poles is fine for that. And then question 10, I asked you to draw the magnetic field around the bar magnet. I'll just come closer to the camera so you can see what I draw. Bar magnet is one of these. I'll label it in a minute, but first the shape of the field. We have this idea that you have field lines emerging from the poles. We have the idea that the field is somewhat symmetrical. In terms of labeling what direction the arrows go, we need to specify a north and a south. So I'm going to put north there and south there. And that means for this diagram, the field lines point from north to south, like that. I hope that's clear enough. So as long as your diagram has this general shape, and as long as it's specified a north and a south so that you can show field lines going from north to south, you've got that right. Half marks if you didn't have the arrows, I suppose, as well, so you can give yourself half. Right, well, work out what you got. Put an answer out of 10, keep that aside. I might ask at the end for you to send me those scores if you'd like to, by email. For now, we will move on though. And this time I'm going to engage some of the comments. I'm going to choose people at random to start answering some questions for me. All of these questions, you're going to see it on my screen in a minute, we're going to be practicing Fleming's left-hand rule. We're going to practice that left-hand rule a number of times. And what I'll do is I'll pick out one person to answer. We'll wait for their answer. We'll see if they're in. If they're not in, I'll choose someone else. And before I say whether they're right or wrong, I'll then ask anyone else who wants to answer to say whether they're right or wrong. So we'll get everyone involved, I think, by doing it this way. So I'm just going to move over to the camera here. You won't see me on the screen now, but you'll hear me talking over it as we've become used to. And I'm also going to try and make sure that I keep it all in shot, because I'm going to be holding this by hand some of the time. So bear with me just one moment as you enjoy my lovely furniture. Right, so what I'm going to do is I'm going to hover over certain questions. And I'm going to hope as I do so that I'm keeping it steady enough that you can see what's what. One main example in, oh, I was going to say the center of your screen. This is already going badly. You can see an example of a circuit in the center of your screen. There is a battery. There are two magnets creating a magnetic field and a wire passing in that magnetic field. Now, there's one thing I'm going to tell everyone. that will help you answer. And it's how we visualize which way the current's going. So in a diagram, in a diagram like this, I'm really struggling. I'm just going to try and keep it on the tripod because this is not working well. In fact, I've got a better idea. I'm going to keep the tripod as it is, and I'm going to hold the piece of paper. I think I might find that easier to say where I'm pointing. I might do. We'll see.